let me put this up while I'm thinking about it. We'll see how you're doing today. Excited, bored, happy. Now that's some real upset right there. That little girl's going to take it to you right there with her little water bottle or whatever she got in her hand. A brush. I think that's a brush. She got a brush in her hands. So she's about to lay it to you there. So there you go. You can put that in the chat. See how you feel today. Thank you for sharing in my excitement on the gender reveal. I mean, that's exciting. That was fun. So we got some threes this morning. Looks like a lot of threes. Just kind of happy. Just kind of, hey, I'm here. All right. Yeah, that's good. We got this. Oh, Laura's a little sad this morning. Jade is bored. Jade is bored. At least nobody's waving a brush at anybody today, right? We're not to the. She's gonna take it to somebody. And that's a pretty good excited there at number one. They got the whole shoulder shimmy going with the So we got a 2 to 3 bored to happy. Okay, I can see that. All right, I got a chance to kind of weigh in there. Fabulous. All right, well, let's go ahead and get started with our lesson today. See what all we're looking at. We're starting a new unit, our last unit of the semester. Let's see, where is 0B? There it is, 0B. Let's take a look. All right, fake student must not have turned in his test last week. His grades dropped. Fake student's got to get his test turned in. So the test was due Sunday. So hopefully you did better than Mr. Fake Student here and got yours turned in. I know there's several of them to grade. I see several of them that are still waiting to be graded. I'm trying to get through those. Have not got those all done yet. So if you've turned it in, don't have a grade yet, I'll get to it. Don't worry. We'll get it upgraded this week. Probably will not be done before grade check because I got classes all the way up until then. So that's fine. Take whatever your grade is in hack or, if I've got it graded, you can take your grade in Buzz, but whatever works. So it's not in hack yet. So this week, let's see. Ooh, look, we just got a few. Module 4 is all we have left until the end of the semester. So if you are behind on stuff, and not many of you are, you guys are doing really well and keeping up. So if anyone's behind on anything, didn't get the test turned in, get that turned in. And I would love for you guys to get all your stuff done by Wednesday and have a really long Thanksgiving break, right? If you get all your stuff turned in, your grades over 70, you'll be in super shape here. So, but today we have exponential and logarithmic functions. Exponential and logarithmic functions. I'm like, ooh, that sounds, yeah, that's not bad. We're going to get into it. We're going to look at it here. So let's go to Unit 4 and just see what they're offering us here. Close Module 3 on to Module 4. All right, exponential functions. So I'm going to pull up my document camera because we're going to do some work. So this starts out talking about a ball. If you ever seen a ball thrown high in the air, throw a ball straight up in the air, right? A baseball, a softball, a basketball, a football, soccer, whatever you're throwing. When it reaches its highest point, it just seems to float there for a second, right? For just a moment, it just hangs there. But after you throw it straight up. So if you haven't seen that, you should go try that. At the top of its flight, it does reach a point with 0 vertical velocity. It stops going up, and for just a moment, it's not moving. It is frozen just there and there. It's stopping and starting to fall back to Earth. And then on the back down, it gets faster and faster every second. The velocity is actually changing exponentially. So let's talk about, before I get into all the stuff that the Buzz has on it, let's talk about exponential equations. Now, we've dealt with equations such as this, right? Like, let's see, make this x to the third power. X to the third power. A little extra line on my x. See, this is not an exponential equation, but it has an exponent. For it to be an exponential equation, the variable has to be the exponent. Exponential. See, that's an exponential equation because the x is the exponent. That's the important part about it. All right, let me highlight that. If the variable is the exponent, it's exponential. That's just a cubic equation, right? That's a third degree equation. That's a cubic equation. It's not exponential. So working with exponential equations, let's remind ourselves of the rules of how exponents work, because these rules are going to work with exponentials just like they do with other exponents. Let's look at the power rule, or the multiplication rule, the product rule. Product rule, that's what it is. Product rule. So if we're multiplying x to the 2/5 times x to the 1/2, and we'll draw a line. This is reviewing what we knew before. Then we can add the exponents. 2/5 plus 1/2, which when we're adding fractions, you have to have them have the same denominator. So 2/5 and 1/2, we can go to 4/10 and 5/10 and add those together. So this is x to the 9/10. So that's the product rule. Remember that, product rule. If you're multiplying two that have the same base, these are both base x, same base, then you can add the exponents. Let's see, the quotient rule. If we are, and let me just divide these out a little bit so we don't get all this together. Quotient rule. If we are dividing x to the 5/6 divided by x to the 1/4, then we can subtract 5/6 minus 1/4. And again, in subtracting, we have to have the same 5/6 minus 1/4. We have to have the same denominator, which in this case we can go to 12ths. So we double this one, 10/12, and that one would be minus 3/4. So we got 7/12. So this is x to the 7/12. So that's the quotient rule. Let's see, what else did we have? We had the power to a power rule. So the power rule, we'll call it. So if you have x, let's just do to the third, and that is being raised to the 1/5, right? So it's being a power taken to another power. Then you could multiply those together. 3 times 1/5, which that's really 3/1. You just multiply straight across. So that's 3/5. So there's our power rule. And the other one that's going to come into play is when we have a negative exponent. So let's say 3 divided by x to the -5th power. That's the same as 3 times x to the 5th power. Because if you have a negative, you can move it on the other side of the fraction. If we have, let's see, 10x to the -2 power, and we don't want to have negative exponents, that's the same as 10 divided by x squared. We can move it on the bottom of the fraction, and now it's a positive exponent. So if it's on the bottom, you can move it to the top. If it's on the top, you can move it to the bottom. See, this is really the top because that's really just over 1. We never write over 1, but every number, every integer, everything's over 1. But that's the rules that we needed to remind ourselves of as we get into, there we go, get into exponentials, because they all use that same rule. So let's see, if we were created an exponential, we were looking at one, if we have an XY table with an exponential, you'd always make sure you have the x's that are just one apart. Right, that's a plus one. That's a plus one. But on the other side, it would be growing exponentially. 2, 4, 8, 16. See, this does not go up the same amount. It's not linear, because otherwise it'd be plus 2, plus 2, plus 2, or whatever. This is times 2. If we look at this one. So this equation is f of x equals 2 to the x power. 2 to the x power is what this table represents. Because if we look at it, when x equals 1, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power equals 16. Notice the exponents. The exponents are the x's. And that equals the 2, 4, 8, 16. So with an exponential equation, this is going to go up 1. This is going to go up exponentially. So let's talk about solving. And again, you get a lot of this in your lesson and other examples, but I want to work some of the things separately here. And then you can look at the lesson, because you can look at the lesson anytime. But let's talk about solve. Let's solve the most simple. Like, let's start with this one we had up here. 3 to the x power equals 3 to the 7th power. I bet you can already tell me the answer. 3 to the x power equals 3 to the 7th power. Well, here's what the shortcut is. Here's what the rule says. If we can get these to have the same base, which they do, right? These are both base 3 raised to a power, then we can cancel those out and just take the exponents and set them equal to each other. X equals 7 in this case, because what equals 3 to the 7th? 3 to the 7th. That's what equals 3 to the 7th. 3 to the 7th equals 3 to the 7th. So x equals 7. We have to get those to the same base. What if we had something a little more complicated? Let's look at something like this one here. I'm going to box this out so we don't get confused. If I have 1 over 256 equals 16x minus 9. Oh, then that looks a little more complicated than that one, Mr. Brogg. Yes, it does. 1 over 256 equals 16 to the x minus 9 power. Solve for x. Well, the secret I said was if we can get these to the same base. Well, so we need to see if we can get this to base 16. And if we can't, can we change both of them to the same base? Well, we're in luck, because in this case, 16 squared is 256. So that means we can rewrite this as 1 over 16 squared equals 16 to the x minus 9 power. Oh, it's not the same base yet. This is still a fraction, and this is a 16. But if we remember this rule right above here, this is the same as 16 to the negative 2 power equals 16x minus 9 power. See, because this is below. If I move it above, it just becomes a negative exponent. Now, these are both base 16. They're both base 16. So I can just set the exponents equal to each other. Negative 2 equals x minus 9. Add 9 to both sides. X equals 7. Because negative 2 plus 9 is 7. And that's the solution to that. So I'm just trying to manipulate these and rewrite one or both to have the same base. And once I have the same base, I just set these equal to each other. Because 16 to a power has to equal 16 to a power. They have to be the same power. These have to be equal to each other. Because 16 to the third power would not equal 16 to the fourth power. These both have to be the third power, or whatever it is. In this case, the -2 power. So to make that the -2 power, 7 minus 9. But that's our goal. We're trying to get these with the same base so we can easily solve it at that point. So let's look and see what our lesson's saying about this. Alrighty. Exponential functions. So it talks about what I was talking about. 3 to the x is, but x to the third's not. So we already covered that. This talked about creating exponential functions, and that looks at it with the table that I already did. 1, 2, 3, 4, 2, 4, 8, 16. So if you want to review that in the lesson, that's right there. Solving, there was the 3 to the x equals 3 to the fifth. I did to the seventh, but so the only thing that equals 3 to the fifth is 3 to the fifth, right? So the solution is x equals 5. Here's the review of the 4 properties. We already looked at that. We already looked at power to a power, but if you need to look at that again, it's right here in the lesson. So it has those reviews for you. So we're already on page 4 because we've covered a lot of this on paper. All right. Oh, here's the one I just solved. 1 over 256 equals 16 to the x minus 9. They have a video of that if you need to watch that again. If you need another explanation, if you didn't quite understand the way I did it, let's see what they're doing. They're changing it to the fourth power. That's another option. Because if you look at that, 256 is 4 to the fourth power. 16 is 4 squared. So they're changing it to base 4. That's another option. And once they get to base 4, they can set it next to each other. But they should still end up at the bottom. Oh, where's it at? Where's their solution? X equals 7. So it doesn't matter. We set them both to the power of 16. They set them both to the power of 4. As long as you get the base, the base of 16, the base of 4, as long as you get the same base, it doesn't matter. You can still get the right answer. So you might want to watch that video just to see how they did it, because they did it a little bit differently than I did. 2 minutes, little 2-minute video. So we're just whipping through this because we did so much already. All right. So here's a chance to participate in the chat again. An application of an exponential function. So suppose you were to find a bottle with a genie inside. Yay, we're all excited about that. That would grant you one of 2 wishes. He gives you a choice. All right, here's your choice. You can either get $100 every day of November. Every day you'll get $100. Or you can have a penny on November 1st. On November 2nd, you get 2 pennies. And then you get 4 pennies, and then you get 8 pennies, and you get 16. And they'll just give you twice as much as they gave you yesterday for the entire month of November. What would you choose? You see, today's the 14th, so you'd have been getting more than a couple of pennies by now. But so choice 1 or choice 2? Do you want $100 every day? Which by now you'd have, let's see, today being the 14th, $1,400 by now. Or do you want a penny, and then 2 pennies, and then 4 pennies, and 8 pennies? Sid says, I'll take $1,400. What do you want, folks? Choice 1 or choice 2? Hey, you get money either way, right? So there's not like a bad answer. Kellen feels like it's a trick question. 100 would be easier to deal with. Okay, I can understand that. Everyone's like, give me $100 every day. Give me $100, man. I'll take $1,400 today. I'm up to $1,400 there. So let's look at that. So how much would you have at the end of November? $3,000, right? $3,000 by the end of November, because you're going to get $100 every day for 30 days. So by the end of the month, boom, you have some good Black Friday shopping by the time Thanksgiving gets here, right? But if you get a penny every day, let's see, you get a cent, 2 cents. Today's the 14th. Today you got 81 bucks, $81.92. But tomorrow you get 163. And let's see, let's see, Thanksgiving is when? It's the 16th, 23rd. On Thanksgiving, you would receive $41,943. And by the end of the month, on the last day, you get $5 million by the 30th. Just doubling that penny every day. Starting with the penny, doubling it every day. You just have to wait a ways. You don't feel like you get so much money for the first couple of weeks, but after that, wow, you'll be loaded. Exponential. That's why they'll teach you in quantitative reasoning, your financial class, that you should start retirement fund early. You start putting money away in your 20s and let it grow. It'll grow exponentially, and you can have a lot of money when you retire. I think if you put like $5,000 in retirement by like 18, it could be $1 million by the time you retire. With good investments, making like an average of 8%. So, all right, exponential growth functions. Here's an example of one. It starts with a penny. This is the example of this function right here. It starts with a penny, and every day it goes up exponentially by 2. It doubles every day, 2. So when t is 1, the first day, after one day, the first day you get t equals 0, which 2 to the 0 is just 1, so you get 1 penny. After one day, that's 2 to the first power, which is times 2. The second day, it's 2 to the third power, but by the 30th, it's 2 to the 30th power. So 2 to the 30th power is 1,073 million. And when you multiply that by a penny, that's where you get $10 million. That's how much you have by the end of the month. If you add every day together, it's a total of $10,737. $10,737 by taking the first 30 days and adding them all together. 2 to the 30th. And here's the chart, the graph. See, the first couple of weeks, you don't get very much, but after that, it starts growing so fast, it's crazy. At day 16, looks like it's off of our graph of 450 bucks. All right. Let's talk about what we really use this for. So really, we use this for like calculating interest. Let's say when we put money in the bank. We'll start a new page, new piece of paper for this. Oh, wait. No, before I get to that, I want to do another exponential problem or two. I want to look at another exponential problem. Before I totally do away with this page, because you have several of these that are going to be in this week's lesson. Assignment. So this is focusing. All right, it's focusing. I'm gonna put one a little trickier here. The square root of 11 raised to the power of 12x. Oh, like, Mr. Brock, what in the world are you doing? I'm making an interesting problem here. Times 121 to the power of x plus 1. You're like, oh my goodness. Square root of 11, 121. Well, this is 11 squared raised to the power of x plus 1. So we can change that to base 11. We can change this to base 11 because the square root of 11, if we remember our rules on that, is the same as 11 raised to the 1/2 power. Remember switching back and forth between a radical and an exponent? And that would be raised to the 12x power. So we have 11 to the 1/2 power raised to the 12x power, and 11 squared raised to the power of x plus 1. So we can go back to our power of a power rules, which means if we have a power being raised to a power, we multiply those together. So 1/2 times 12x. So this is 11. 1/2 times 12x is 6x. Now over here, 11, 2 times x plus 1 is 2x plus 2, right? When you distribute it into the parentheses, 2 times x, 2 times 1. Now, hey, we've got the same base. So with the same base, we can take the 6x right there and the 2x plus 2, set them equal to each other, subtract 2x, 4x equals 2, divide by 4, x equals 2/4 or 1/2. X equals a half. So x equals a half in this equation, those are equal to each other. So when to solve another one that looked a little more complicated before I move on. But now let's move on to what we were looking at on the other exponential, the real life exponential that you will see often throughout life. Well, only if you pay attention to your finances. I'm going to write this formula here. This is great for your notes because you'll be using this formula right here. Okay. A equals P times parentheses 1 plus R over N parentheses raised to the power of NT. You're like, man, there's no numbers to work with, Mr. Brock. It's all, yeah, you're right. So A is amount. So if you want to know the total amount of money you're going to have, P is your principal, not Miss Scott. This is actually spelled PLE, which is your starting amount. Okay, that's your starting amount. That's what the principal is. R equals rate. And you need to make it a decimal. And we'll talk about that in just a moment. N, number of times per year you get interest. And T is time in years, usually. Not always, but usually in years. If you're looking at it like an investment, like if you have money in the bank, T would be years. So let's look at a sample problem. Let's just make up a sample problem. You're going to invest $1,000. You've saved up $1,000, and you're going to put it in the bank. Oh, my monitor's trying to go out on me. All right, it went black, but it came back. Okay, and you're going to get, let's say, 6% interest quarterly. Now, let's say it's in a savings account, so they'll give it to you every month. How about that? Every month when you get your statement, they will give you, it's in the savings account, that they're paying 6% interest monthly. And we want to know how much money we'll have if we leave it there for 5 years. Okay, so that's a typical investment problem. I'm going to put $1,000 here. I'm not going to pay any attention to it for 5 years, and they're going to pay me 6% interest every month. So how much will I have after 5 years? Okay. Well, just if we ballpark it and think, okay, we should have some idea of how much we would expect. So we don't want them to cheat us. We should have some idea. If we know if we make 6% interest, 6% of 1,000 is $60, right? $60. So if I make $60 a year for 5 years, I should make $300. So if they're not giving me back $300 after 5 years, somebody's cheating me, right? All right, 6%. We can pull up our calculator here too, because we're going to need to calculate a few things. So 6%, we have to remember, has to be in decimal. Let me move this out of the way. I said your rate has to be a decimal. What is the decimal of 6%? So 6% is the same as 0.06. 0.06. So if we said, okay, well, $1,000 times 6%, 0.06, see, $60. So I should get $60 a year. But let's see what the monthly interest does to me. Because here's the thing. They're not going to wait and give me the $60 at the end of the year. They're going to give me 1/12 of that. That could be $5 after the first month. So that means the second month I'm getting paid interest on $1,005. Because if they give me 1/12 of it, the 60 divided by 12 is 5. So after month one, I've got $1,005. So they're going to calculate my interest based on this. So I'm going to get a little bit more than $5 the second month, right? Because I've got a little bit more money than 1,000. So it's going to add up a little bit extra. But let's see how much. Let's use our formula here. So we want to know what the amount is going to be. If we start with $1,000, that's our starting amount. That's the principal. 1 plus, now remember, the rate has to be as a decimal. 0.06 divided by n. What's n? The number of times per year you're getting interest. Monthly would be 12 times a year. To the power of 12 times how long? 5 years. 12 times 5. All right, so let's simplify this so we know what equation we're looking at. So it's 1,000 times. Now let's do this math. Let's bring our calculator back up. So we have 1 plus, and then we're going to divide this. I'll put it in parentheses. 0.06 divided by 12, parentheses. Okay, so there it is, 1.005. And then 12 times 5 is 60. Okay, so let's do the next step of the math. So now we're going to say it's the original $1,000 times what is 1.005 to the 60th power. Let's see, 1.005, and I'll hit this XY, taken to the power of 60. 1.348885. That's probably enough decimals. We'll go 5 decimals. So times 1,000. So we will have $1,348.85. That's how this works. So this is great to have in your notes, this formula, along with what they mean, so you know how to use it. You might have a good example of how to write percentage as a decimal, and you might even have a sample problem in your notes. So if you're doing this on a test or anything, you've got your notes you can pull out and say, oh, I have one of those. I can look and see what I did there, so I can do it on this problem. So for monthly, n equals 12. All right, put this in the chat. If it says it's compounded quarterly, what does n equal if it's compounded quarterly? Because a lot of times you'll see that. The interest is compounded quarterly, so what is your n? Oh, Laura says it's 3. Sid says it's 4. This is the number of times per year you get interest. That's what n is. So if you get it quarterly, quarterly is every quarter, which is 3 months. So yeah, it is 4. N would be 4. because there's 4 quarters. 4 quarters in a year. 4. Let me write that for you. N equals 4 if it's quarterly. So make sure, yeah. A quarter is 3 months. So we that's why I wanted to write this in our notes, because we get confused about that. A quarter, how long is a quarter? That's 3 months. Yeah, but that means there's 4 quarters in a year. So we need to go with the 4. So don't get confused and think quarter's 3, because that'll mess up all your calculations. So, and that's easy to do, to think 3, because a quarter is 3 months, and we get that 3 in our head. So I don't want you to make that, just because that's a real easy thing to think. How long is a quarter? 3 months. Yeah, 3 ends 3. No. Think it. You've got to remember, it's number of times per year. So there's four quarters in a year. So just put that out there so we don't get confused, because that's an easy one to miss. So good job. All right. You also have a case where you can have decay. And that means, like, if you buy a car and it goes down in value. So let's look at one of those examples. Let's say you buy a car that is worth, you spend $20,000 on this car. Okay. And that's got to be a used car. You can't get anywhere close to a new car for $20,000. So you have a used car. Here, let me turn the light. Maybe it'll focus better. It's not focusing real well today. And it's going to depreciate 20% per year. And at the beginning, it would. When you buy a car, especially a new car would depreciate 20. We're going to pretend you can buy a new car for $20,000. It's going to depreciate. How much would it be worth after 3 years? Some people like to buy cars every 3 years. They like to spend a lot of money. But I know people that do that. They trade cars every 3 years. I'm like, that is costing you a fortune by buying a new car every 3 years. Buying a used car every 3 years, be better off. But let's see what that would do to us. And this is just per year, 20% per year. Per year. So when we talk about depreciation, that's usually just once a year. So we would say the amount equals 20,000 times. Now, in this case, since it's per year, N is 1, right? Because we're talking about once a year, it loses 20% of its value. And R would be a negative number. So negative R. So if it's 20%, the decimal for 20% is 0.20 or 0.2. So 1 minus 0.2, and again, N is 1, because we're talking about once a year, for 3 years to the third power. So we're talking about 20,000. 1 minus 0.2 is 0.8 to the third power. What is that car worth after 3 years? Let's put our calculator up. Take a look at that. Clear. We'll do the 0.8 to the third power first, and then take that times $20,000. After 3 years, your car is worth $10,240, and that's pretty accurate. A car will lose about half of its value in 3 years when you buy a brand new car. A brand new car will lose about half its value. So if you're buying a new car for $50,000, in 3 years, it's going to be worth about 25, maybe 28, somewhere in that range. And your payments, you probably still owe 35 at that point. So just knowing that cars are very, very expensive. If you buy them new, you're better off buying used, where it's already lost a bunch of that value. So you can get there and you can get a car that's 3 or 4 years old and pay half of what they paid it when it's brand new. And you're not going to lose as money as fast. So tough thing. I'm buying a car now myself. My wife's car died last week. The transmission went out, and so we have to have another car. But I'm not buying a new one. I'm buying a used one. And yeah, even used, they're a lot of money. Right now, especially, they're just crazy high. So basically, for depreciation, and you see this a lot if you're in science, like you'll have some bacteria or something, well, bacteria usually grows, but I mean, you'll have stuff where it decays at a certain rate, and it's usually 1 minus the rate over the amount of time. See, but let's introduce one more thing about decay or interest. There's something about continuous, and this is crazy. If you can imagine getting continuous interest, like every second they're giving you new interest, compounded continuously. Nobody does that because that's just crazy math. But compounded continuously, we have to bring in another number for that. Another number. And here's what that number is. The number E. Like Mr. Barack, you wrote a letter. Yeah, well, in math, this is a number. Just like in math, I is a number, right? We know I is the square root of -1. E is like 2.71, or let me look at it. We don't use E very often. There it is, 71828, 828 dot. It goes on. Our calculator is familiar with E. If we clear everything, there's an E right there. If I hit E, see, there's E. 2.7182818284590. It's like pi. It never ends. It just continuous. It's a number that goes on forever there. It doesn't end, but it's a number that we use in math. And so if you use E, if it's compounded continuously, you use E. And let's see, where's the formula? There it is. Let me write this down because they may ask you a question about this. It's not really real life because no one's going to give you continuous, but the amount you would get would be the principal times E to the RT. That's for your notes. Compounded continuously. Compounded continuously uses the principal times E, which is that's not a variable, that's a number. It's 2.71828 blah 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 to the power of RT. The rate in a decimal, whatever that rate is, times the number of years that you're looking at. Compounding continuously. So, we're going to make sure you were aware of that because it talks about it. And you can go through it here at our lesson. It'll talk about $500 with the interest rate is 6% per year after 3 years. Let's see what it has. You put the 0.06 in, you put the 3 years, you put it 3 times the 0.06 right there is 0.18. Oh, my monitor's, there it is. Okay, 0.18. So $500, put this in your calculator, 500 times E to the 0.18 power. E to the 0.18 power is 1.1972. So you'd have $598 after 3 years. That's pretty good. Compounded continuously. But that's how you use E. And then they round it off to the nearest penny. And so it says there's the answer. Here's more examples of exponential growth if you needed to see more examples. And it uses PLERT, where L is the initial population. So instead of A and P, it's using P and L, but it's the same formula. And so this is the population. You might use E because it is continuous growth. People are always moving in, like Northwest Arkansas. They use this E calculation for that. And so they figure out how many people can be in there. A bacteria would use continuous growth. If you get into science, because it triples in size every day. So they're creating a function for that. And see, it grows really fast. Number of bacteria after a week, 21,000 when they started with 10. Because continuous growth of bacteria. All right. Was there anything else in this lesson before we get to logarithms? And that's the exponential decay. It's the 1 minus r. We did that with a car. 1 minus r. So we have that. We have that in our notes as well. That formula for decay, that for continuous. Here we'll write decay by this one. Decay or depreciation, where it's going down. All right, let's look at our. We can look at the assignment real quick for exponential. Which exponential function represents the data? So it's going up by 1. So what's the multiplier here? So you got to figure out which one of these equations would that be. Solve this. You need to get them both the same base. You got a base 8 and a base 2. So I'd rewrite the 8 as a base 2, and then you can solve that. Base 64, base 16, you probably need to change both bases there because 64 is 4 to the third, where 16 is 4 squared. 1 over 25 and 5, so you could change that. Oh, there's one of the square root ones, but you can change that to a 6 to the negative 2 power, and you can change that to a 6th power 6. Oh, here's a compounded monthly equation. So there's where you use that interest with the 1 plus r over n. This one's compounded continuously, so you got to use that P-E-R-T, compounded continuously. 4 bacteria double in size every hour. So again, it had that bacteria example in there. If you need to go back and see what formula they'll use for that, go look at that bacteria example. But they used the P-E-R-T, except they made it L-E-R-T. A jet ski depreciates at 11%. So this is the depreciation, the decay formula, the 1 minus r. And a hospital is given 50 milligrams of medicine, which leaves the bloodstream at 10% per hour. 10%, 0.1. So this is also decay. That's another place it's used in medicine because your body's filtering out that medicine. So figure out how many milligrams remain in your system after 6 hours. All right. So there is the 10 problems for exponents. Let's look at logarithms. And you may think, all right, why do we need to know logarithms? Well, I don't want to teach you addition if I don't teach you a subtraction. I don't want to teach you multiplication if I don't teach you division. Well, exponents and logarithms also are inverse functions of each other. So, this is interesting. In the 1930s at the California Institute of Technology, Charles Richter developed the Richter scale. I wonder how he came up with the name, huh? Which describes the severity of earthquakes. So you'll hear when they have an earthquake, it was a 5.1 on the Richter scale. So he has a device called a seismograph that they use, and it's got a needle that vibrates back and forth. And there's kind of what it looks like on a printout. It goes back and forth. And the more the needle vibrates, the stronger the earthquake. So the distance that one needle vibrates from the top to the bottom is known as an amplitude. And they take the logarithm of that amplitude, along with other measurements like how far away was the earthquake from the seismograph, because that affects it, to determine the measurement on the Richter scale. So the Richter scale uses logarithms. So there is a lot of use for logarithms out there in life, but it is the opposite of exponential. It's an inverse function of exponentials. So let's see what they say about that. So if you were going to graph this function, this is linear, right? We know how to graph linear. We've been doing that since junior high. 2x plus 3. The 3 is the y-intercept. The 2 is the slope. So it goes up 2 over 1, up 2 over 1, rise over run. If we took the inverse of that function and graphed it, it would look like that. It would be a reflection over the line y equals x. That's the inverse. Inverses reflect over the line y equals x. Okay, so that was with linear. We've done that. But with an exponential equation, here's an exponential equation. It's 10 to the power of x. If we reflect it over that same line, y equals x, this is the inverse, which would be y equals log x. 10 to the power of x and log x are inverse functions of each other. And we see that when we graph them, because they graph as a reflection over that line, y equals x. So let's talk a little bit about logarithms. Getting started here. I'm going to switch back here. So you'll see y equals log 100. And we'll say something. What's the answer there? Or maybe you'll see y equals log 327. Which, by the way, this equals 3. This equals 2. Y log 2 of 32. That equals 5. And you're like, what in the world are you doing, Mr. Brock? You're just throwing numbers out there. That doesn't make any sense. Well, once I explain how logarithms work, it'll make a lot of sense. Let's see. Where did I put my notes on logarithms? I was doing those yesterday. So I can show you. There it is. Okay, so here's how logarithm works. And you're like, okay, I noticed something though, Mr. Brock. You put a 2 here, you put a 3 here, but you didn't put anything there. That's correct. I did not. Because much like if we put x equals 5 and we put 2x equals 10, why did I not put anything in front of there? Because that's assumed to be a 1. Well, with logarithms, this is the base 2, base 3. If we don't put a base, it's assumed base 10, because that's what our number system is based on. We have a base 10 number system, right? We use a base 10 number system. If I don't put anything there, it's assumed to be a 10. And here's how this all shapes out. So let me get some different colors here so I can kind of illustrate this better. All right. If we have this exponential equation, y equals a base number raised to the power of x, okay? Y equals a base to the power of x. This is exponential, right? Because we've got an x up here, exponential. The logarithmic equivalent of that would be x equals, and let's see, I'll just write this in pencil. Log, the base is going to be the same. That's the base. This is the base. Log base what? Log base y. And I color coded those for a reason, because if I have this, let's actually do one then. Let's say, all right, so I have, we'll say 49 equals 7 squared, right? That's correct. 49 equals 7 squared. Well, the logarithm equivalent of that, and I'll write it in the same order I put there. 2 equals log 7 of 49. See how those relate to each other now? If we say 7 squared equals 49, that means the log 7 of 49 equals 2. So a logarithm is basically saying, like looking at this one right here, which it's going to bleach it out there. Okay. Log 3 of 27 means 3 to what power would be 27? what does that equal? Log 3 of 27. 3 to what power is 27? Because if we convert it to here, base, 27 equals 3 to what power? We don't have the x. 3 to what power? Well, 3. 3 to the third power is 27. That's why that equals 3. That's why this log 100 equals 2, because 10 squared is 100. Log 100 equals 2. I think our calculator has log button. Yeah, it does right there, log button. This is automatically base 10. Most calculators have base 10. You may have a fancy calculator. See, if I hit second, it lets me put a base in as the y. But if I don't put a base in, I'll say, okay, how about 1,000? What is log of 1,000? Well, it's 3, because 10 to the third power is 1,000. But a lot of times you may have 52, log of 52. Well, if you take 10 to the power of 1.716000343, it equals 52. So logs usually end up with some kind of number like this because it's not always a perfect square, a perfect cube, or something along that lines. But your calculator will figure out what the log is. But you need to understand what the log is. So let's see, how do we use that then? Okay, well, let's see. Let me put a problem here, and we're gonna solve a problem for x. So you might have a problem like log 5 of 1 over 625 equals x, and you're supposed to solve that. And you're like, ooh, well, the easiest way to solve a logarithm is to rewrite it as an exponent, and then we can use our exponent rules. So look at it. What's the base? Well, the base is a 5, so I'm going to write this as a 5. What's the exponent? Well, it's the x on the other side. On a logarithm, the x is over here. So 5 to the x power equals y, which is whatever the argument is here. 1 over 625. Okay, so now this looks a lot easier to solve than this does, because we take it, a logarithm, and rewrite it as an exponent. That's why you need to know where the pieces all fit. Okay, so 5 to the 5th power equals, well, what's 625? Let's see, 5 to the first power is 5. 5 squared is 25. 5 to the third is that times 5 more, so that's 125. 5 to the fourth is that times 5, so it's 620. Okay, so that's 1 over 5 to the fourth. Oh, wait, this shouldn't be a 5. Don't let me write the wrong thing. This should be an x. The x is the x. Trying to solve that, not 5 to the 5th. 5 to the x. Gosh, don't let me make mistakes here, guys. We take the 5 goes with the 5, the x goes with the x, the 1 over 625 goes over here. And I'm solving this for x. Solving this for x, which is right here. So 5 to the x equals 1 over 5/4. We know we can rewrite this as base 5. 5 to the x equals 5 to the negative fourths. That's why we bring that up on top by making that a negative. So x equals negative 4. So that means x equals negative 4 here. Log 5 of 1 over 625 is negative 4. Let's try that with our calculator, see if our calculator agrees with that. Since our calculator will, if I do second, it'll let me do the base. So if I say 1 divided by 625, and then I hit this, and I say base 5, it's got 1/4. Why does it have 1/4? I may have done that backwards on there. The x and the y. I'm not sure how to use this. I haven't used this calculator to do this. Let's see if we go log x. 1 divided by 625 log. Oh, it's divided. Oh, I see. I didn't put it in parentheses. It went 1 divided by that. Parentheses. 1 divided by 625 parentheses. That is what I want to take to log base 5. It's -4. Yeah, I didn't put it in parentheses. So it was taking my answer and dividing it by all that. So yes, it is -4. 1 divided by 625 log base 5 is -4. Because we just solved it right there. Let's see. What else does it show us in there? Oh, of course. Also, you can have a logarithm with base e. This is called the natural logarithm. So let me point out something on this calculator. See, it's got log right there. Underneath it has ln. That's also log. That's also log. You're like, that's also log. What in the world? So if we just have log of a number, that's assumed to be 10, right? Assumed to be 10. Other thing, you can have log e of a number, 7. Let's just throw a number. But you don't ever write it like this. This is called the natural log. E is called a natural number. It's written as this, ln 7. When you see ln, that means log e. ln means base e. It's a logarithm with base e. Those mean the same thing. But this is how it's written in math. If it's log base e, it's written as ln, the natural log. So let's play with that just a minute to kind of prove that to ourselves that works. So if I have, let's look at log 7 here. So if I take the natural log of 7, it's 1.945. 1.945,910. Okay, so I've got that written down. 1.945, and it continues on from there. Let's do log base e of 7. So if I do 7, and I'm going to use this log y to the x button, and it wants to know what base, and I hit the e, base e. Look, it's 1.94591. That's the exact same number. I just did the actual log button with base e rather than just doing the natural log button. So the natural log button is right there. Now look at it. When I hit the second, it has e to the x, which is the exponential version of the same thing, right? E to the x, which will take us back to 7 because it's opposites. So if I take e to the power of 1.94910, it equals 7. So let's see what our lessons tell us about that. Okay, here's the conversion that I did on our notes. Y to the bx equals x to the log by. So you definitely want that in your notes. How to switch back and forth. It's how you switch back and forth. If you have it logged, turn around and write it in exponents, and then you can solve it using our exponent rules. And if you want an example, you can put this in your notes, because that's an example using numbers. All right, so let's go back to this right here. This is the terminology. With log 3, 9 equals 2. 3 is the base. Log base 3, as I've been saying. 9 is called the argument. That's that number after the log. Argument. And then 2 is the exponent. Because when we rewrite that, it's 3 squared equals 9, where 2 is actually the exponent and 3 is the base. 9 is the argument. So, all right, so if you created a table of a logarithm as opposed to an exponent, it's just the opposite of what we saw in the last table. See, this has the y version, f of x, which is the same as y. It goes up by 1. 1, 2, 3, 4. So plus 1, plus 1, plus 1. This one goes up exponentially. 2, 4, 8, 16. So that's just the opposite. When we had the other table, we had 1, 2, 3, 4 on this side, and this one up 2, 4, 8, 16. So when you substitute 4 in, you get 2. When you substitute 8 in, you get 3. When you substitute 16 in a logarithm. So you're seeing the x's go up times 2. And that would be f of x equals log 2 of x. log 2 of x right there. And you can check those two. If I substitute 2 into log 2 of x, it equals 1. If I substitute 4, it equals 2. If I substitute 8, 2 to what power equals 8? 3. 2 to the what power equals 16? 4. So you could create logarithm tables that work the opposite of the exponent tables. Okay, and here is the problem that I've already worked. Log base 5 of 625. They have a video if you want to watch that again. If you didn't quite get how I did it, you'll see it equals -4. They'll work through that and show you all the steps again. So, all right. Oh, this is the lesson summary. This is the end of it. So one more, log B of 81. Oh, I like this. This is putting the variable in a different place. Log B 81 equals 2. Puts it in a little different area. Log B 81. So let's rewrite that first. Remember, the base is the base. The exponent is the exponent. 81. We need to find B, and it's being squared, so we'll take the square root of it. So B equals plus or minus 9, except since it comes from a logarithm, here's an important rule. Base of a logarithm can never be negative. So we would throw out the -9 and B equals 9. Because 9 squared is 81. We would throw out the negative one, because when we take the square root of 81, it is plus or minus 9. But since the base can never be negative, never negative, base of a logarithm, we throw out the negative answer. So that was the last example they have there in the lesson. And then they have the lesson summary. So both of these lessons have sample problems for you to try. So that way you can check out and make sure that you understand what you're doing before you take the assignments. Let's look at the second assignment real quick. Start one. Oh, wants to know which log function is in the table. Remember, it's just the opposite of the exponential. Evaluate this. Log base 7 of 343. Log 2 of 1 over 64. Log of x minus 1. Base x minus 1, 16 equals 4. Just rewrite these as exponents and then solve them. Log x equals 4. Rewrite these as exponents and just find the missing piece then. So, all right, guys. It is last week before Thanksgiving. So next week, we got all week free, so get things done early this week to make your break longer. Why not, right? That's what virtual school is all about. Make sure your grade's over 70%, everything's turned in, and you're party on. If you need to see me, Friday, I will be here. I will not be here Thursday. I have to go to my oncologist in Little Rock just for a checkup. Everything's good with the leukemia, as far as I've been told. But no, I expect everything to be fabulous. I just have to go in for a checkup in Little Rock. So I will not be here Thursday. No class Thursday. But anyway, we will see you guys after Thanksgiving. Have a fabulous time. See some family, play some games, eat too much, all the usual. And we'll see you in a couple of weeks, unless you need to see me Friday.